Okay, so thank you very much for inviting me and giving me the opportunity to make this presentation. So apology, we are 13th of December, not the 3rd. Okay, so yes, RTE is a French transmission operator. We own and operate 100,000 kilometers of lines, which makes us the largest in Europe because, but well, I mean, France is not the larger country in Europe, but depending on the organization of the electricity sector, power sector in each country, you might have several companies or one company doing what we do. Okay, so we are a big company operating 60 kV to 400 kV lines. In some countries, for instance, in UK, in some parts of UK, 60 or 90 kV grid is operated by the distribution company. So this kind of grid, 60 to 90 kV, I will name it sub-transmission. Okay, and this is in this sub-transmission grid that I will present the work today. Okay, so now I will have my talk in two parts. First of all, I will take the talk I made 2 years ago in Florence in January 2020, just before pandemic, just to give the context, and then we will go to this one, sub-transmission grid optimization, to see what it gives in reality. Okay, so now I will switch back. I will switch to only a few slides, which are part of what I presented in Florence in January 2020. Okay, can you see the screen? Yeah, so this was my talk 2 years ago. Okay, so this talk was solving alternative current, so AC, optimal power flow to global optimality. Okay, this is the talk of Adrien Godard, who defended his thesis end of 2019. Okay, so this is the electric grid, and here you have demands. Can you see? Yeah, demands here, like D or load or consumption, the equivalent for demand. So what is being consumed either by large industries or by distribution network. So here it looks like a simple client, but in fact it's a distribution grid, many kilometers of 20 kV grid and 230 volts grid. And this is generation. These are all complex variables. Okay, so here you have real part representing active power and imaginary part representing reactive power. Okay, it's a way. The idea is you have two waves, one wave on the grid for current, one for voltage, and they are not synchronized. Okay, so it's 50 Hertz waves of current and voltage. They are almost never perfectly synchronized. There's an angle in between. This angle creates a real part and an imaginary part. So here we have complex numbers. Voltage are complex, currents are complex, powers, so apparent powers are complex, with the real part being the real active power and the imaginary part being the reactive power. We have physical laws, and of course, and the main control variables are generated power, the demanded power or loads are usually an input of the optimization problem. And we have security constraints, so bounds on voltage magnitude. Okay, so you have a complex variable and bound on its modulus. The goal is usually to minimize the cost, linearly linked to active generated power, so to the real part of the generated power. And sometimes all these coefficients are equal to 1. In that case, you simply minimize the amount of power, which is simply losses minimization. Okay? Because roughly you have the demand plus the losses, the Joule effect losses, equals the generation. And this leads to this kind of formula to get the flow on the lines from the voltage. So you can express everything with the voltages. Okay. So at the end, when you see this, so this is the line from I to J. This is the ground. So this models the interactions of the lines, underground lines or overhead lines with the ground. This is the line itself. So this is a complex number. So the active part is represented is the resistance. So gives losses with Joule effect, and the reactive part is named reactance, and it models the fact that this device, that this line here, is creating is participating to the unphasing or to dephasing the current and the voltage. Okay, so the phi angle between the current and the voltage in I or in J is modified by the reactive part of the impedance. Okay, so here you have the flow here, the apparent power flow, and everything here is complex numbers. So here you see already that we have quadratic terms, okay, in complex numbers. So everything may be written as a quadratic non-convex problem. Here the matrices are symmetric but not semi-definite positive. And we can go, of course, to real model with real and imaginary part. Okay. So here the modulus of or the amplitude of the complex voltage will somehow be a sum of square of real variables, and then this part will be non-convex. This problem is named ACOPS, so alternative current optimal power flow in NP-hard. With interior part method, we have very good solution, feasible solutions. And with conic relaxations or semi-definite relaxation, we have good lower bounds. Okay. Okay, so this was the you see these were the first slides of my talk in January, and now I jump to the conclusion on the same talk. So where are we on this AC optimal power for global optimality quest? We have many works with near optimal solutions, and they don't give any real improvement compared to interior point methods. So as the conic approach and SDP approaches are new, people compute an SDP relaxation or conic relaxation, and from this they compute a feasible point. But you could get the feasible point with interior point methods. Okay, so the feasible points are not better, or there is no improvement as of if we compare to what we can do for 20 years already with interior point solvers. Okay, we also see a lot of work saying, well, we can solve optimal power flow to global optimality. And you see the paper, and the criterion is always 1%. This is Americans, okay? Because Americans, they use these kind of problems with cost of power, and as a cost, 1% may be seen as important, as near optimal. 1%, but maybe 1% is not that optimal. Okay, if it's in billion of euros, 1% is maybe not that good. We in Europe, we are technical engineers. We are not business people. Okay, so we want to minimize the system, whatever the cost is. Okay? Or basically, the cost is handled by something else, and we, the TSO, we try to optimize the system. So we try to optimize losses. Okay? Because roughly the costs are we are already fixed somewhere. Okay, so we really try to minimize the losses, and then the losses are usually 2%. So what if you have a 1% optimality, but you know already that anyway the losses are roughly 2%. So it's not 1%, in fact, it's 50%. Okay. So the American approach for this works to have a 1% optimality. From our European point of view, it's bad. It's really not enough. The global optimality is not, well, I have a 1%, and then if I can solve all 90% of academic instances to 1%, I'm fine. Okay, so this is not correct. So global optimality is you choose some feasibility criterion, some optimality criterion, and then there is a method that will find a global solution to this pre-decided or decided by the user criterion, whatever long it takes. Okay. This is the global optimality. But in the power system, which are basically led by US researchers, it's very difficult to explain. So what is possible to do today for global optimization, for AC global optimization? So there is a laser hierarchy, okay, full or partial. It's possible. Here, if we look here, we have the number. This n here is the number of buses or the number of electrical nodes in a grid. So in France, on the French grid is 6,000. Okay, 6,000 here. So here the number for real variable are 12,000. Okay, and we are speaking about SDP relaxation of this. So I already asked the question 2 years ago. Is it possible? Do you think it is possible to solve the SDP relaxation of this problem? Okay, so 12,000 real variables. Okay, so so I already asked this question 2 years ago. So will anyone be able to give an opinion? So here in the room, to your opinion? It depends on the structure. Okay, thank you. This is exactly the good answer. Basically, basically there is an underlying grid, a graph. Okay, so there is a grid, and so there is an underlying graph of relationships between coefficients. Okay, so here the problems is sparse and structure. So we can do decomposition, chordal extension, cliques, etc. Okay, that is why it is feasible to solve the SDP relaxation, or it is feasible to solve the rank one, the first order of the laser hierarchy, which are similar. Although there is a although. The precision, I mean, with large problems, the epsilon you have at the end is not always reached by the solver, MOSEC solver or another one. And it happened that if you don't look very precisely, the lower bound you get with the SDP solver is higher than the upper bound you get with interrupant solver. Okay, this means that there is a problem somewhere. So numerical precision is really an issue here with SDP solvers. So we have a student working on it in École Polytechnique with Léo Liberty. His name is Antoine Oustry, and he made some work to tackle this issue. Okay, so other methods, spatial branch and bound, either SDP or conic. So at each node of your spatial branch and bound, you have an SDP or conic relaxation to solve, or this was the work of my student Adrien Godard. He made a branch. He used an SDP problem to reformulate to a quadratic relaxation, for which at the root node, the value of the relaxation was the same than the SDP relaxation. Okay, so he was starting from the same point as an SDP branch and bound, but with a quadratic problem, convex quadratic problem to solve at each. So global optimization is not so important from economic point of view. So why do we, RTE, care about global optimality? 2 reasons. So first reason is these equations, they are not only complex equations with complex number, they are also complicated. Okay. We use these same power flow equations in simulation tools, either static simulation tools or continuous time domain simulation. And then we think that making progresses with the solving of these equations will be a general progress for our power flow management business. And second, if we have really the global optimization, then we could embed this into larger computation or simulation tools that need global optimality criteria. Okay, so this was for AC optimal power flow. Okay, so here we RTE, we do some research, we found some research for this AC optimal power flow problem. And now what do we do in practice? So I will switch to the practical project part of the presentation. So here, keep in mind here that here we have complex numbers, and this is quadratic. Okay, so the Z here, they are constants, impedances. So here it's only the quadratic part which are here. Okay, so let's go. Okay, can you see the screen outside? Can you see the okay. So here, my talk is about model predictive control framework for congestion management with large batteries in sub-transmission grid. Sub-transmission means 60 kV to 90 kV part of the grid, which is meshed. Okay, it's really it's not a tree, it's really a graph, and it is connected to the very high voltage grid, which is 225 kV, 400 kV. And here we are starting, well, we are in the middle of a project for automatic congestion management with large batteries, but also renewable energy curtailment or limitation. Okay, so a congestion is when you have too much power on the line, you reach the capacity of the line. If you reach the capacity of the line, then the line with Joule effect becomes too hot, and then with dilatation, it's beginning to be dangerous. So the line becomes longer. When it's hotter, the metal is longer, so the distance to the ground, so the clearance to the ground, becomes too small. And when people are walking there or vehicles are driving there, they may get some lightnings, okay, and they may be killed simply. Or in some cases, the equipment, if it becomes too hot, when there is a junction between two parts of the equipment, this junction, if it's too hot, the junction is malfunctioning, so it may release the two parts of the equipment, and then the line may fall to the ground. So this is less dangerous because it falls out to the ground, but basically there was nobody here usually. Okay? I mean, the fall to the ground was not due to someone coming there. And then some protection will immediately switch off the current, so it's not so dangerous. And this happened. So the fact that someone is injured or killed walking under the lines, to my knowledge, it never happened in France. Or error, so a fissure, or someone carrying a ladder, okay, or irrigation or water pipes, little water pipes. So when there is no error, I'm not aware of any people being injured, but it happened already that lines fall on the floor because there was too much power in it. Okay, so this is a congestion when there is too much power. So basically, there are upper bounds on the amount of power you can put on the line. So this is a work made for a few years already with Centrale Supélec, Professor Soreno Larue, Alessio Iovine, chargé de recherche NRS. Clémentine Straub defended her PhD recently, and now she is a pilot, a plane pilot with Air France. She did not say with academics, but well, she should get her pilot degree in December, in about 2 weeks. We had a cooperation with Stanford University, and then in RTE, we are many people working on it. And part of this is supported by the CPS for Europe, so Cyber Physical Systems for Europe, European project. So background, we want to connect more renewable energies than feasible. Okay, that's the goal, and that's what we have been doing for already many years. Okay. So the official policy shared with authorities, local and national authorities, is to connect to the grid more power plants, so renewable energy power plants, than grid capacity. May seem, I mean, the goal of this slide is to explain why. So why? Intermittent renewable energy, so solar and wind, obviously they are not producing 100%, they are rarely producing 100%. If you look at the solar plant in winter, it will be never 100%. If you look at a wind farm, it might be at 100%, but very often there is one of the mills is there are construction works or some planned outage or something. So globally, it is rare that they are all of them operating at 100% of capacity. So when may congestion occur? Okay, so congestion is when there is too much power on the line, or reach or near to or almost too much power. It's when you have low consumption. Otherwise, the power stay at the same place. Okay, if you have a high consumption with a high local generation, then no issue on the transmission line, because the power stays at the same place. But when you have a very low consumption, let's say by night in August, in a windy area, the consumption is very low. When you have high temperature, okay, so in summer, the capacity of the line is reduced because the overall the temperature outside is in average higher than in summer. So there are some computations, they are not perfect, but they give the upper limit of the flow on the line lower than in winter. Okay, this is named seasonal rating. Okay, so the rating of the line, so how much current you can put on the line, depends on the season. And if it's very hot, if you have 20 or 1 week with very hot weather, then they reduce even more. Okay, there is something like an emergency, very low rating in case you have 35 degrees for days. We also have dynamic line rating in some places. So that's a device that is measuring on real time the heat of the line, and then you can adapt the flow to the temperature on the line, which is measured on the line itself. And then the third point for congestion in this kind of sub-transmission areas is when you have high renewable energy generation. And then what can we do for this? Either we build new lines or we do renewable energy curtailment. Okay, so I will ask you advice. Okay, so you will answer. Okay, so who in the room is for option 1, building new lines? Please answer. Who is for curtailing renewable energy? Please, you have to answer. Okay, so we will do it the second time. Okay, you have to say one of the two options. Okay, so all people in the room, who is for option 1, building new lines? High. Okay, 2%. Okay, who is for curtailment of renewable energy? 2%. No, you have to make a choice. Please make a choice. Okay, so third time we replay. Okay, who is to build new lines?
Nobody will be, there will be no sequences.
Who is for renewable energy curtailment? Oh, you're cheating, guys. Only 2 again. Oh, yeah. 3. Okay. So we decided together with authorities to go for the second option. Okay, and the savings here is 7 billion, estimated saving in 10 years. Okay, 7 billion. This is official document. It's written in the 10-year development plan of RTE, which is agreed by national authorities.
I mean, if it turns out to be wrong, I mean.
It's a saving. It's an estimated saving. Okay. So basically, we save the price of building new lines. Okay, and we pay some penalties when we curtail the renewable energy. Okay, so when we ask the wind farm to stop because there is too much power on the line, or when we ask to some solar farm to reduce the generation, then we pay some penalties. Okay, our estimation is that we will be able to have at maximum 0.3% of the energy in average at the national level. Okay, and this 0.3% of energy will be the cost of our penalty. And what we gain, what the saving is not building new lines. Okay, and the sum of these two is 7 billion. Please, yes, you have a question.
When I think of the only electrical cars, I think anyway for.
Okay, so the question here is, as I said that we have congestion when low consumption occurs. What if consumption is increasing? Of course, we have many hypotheses. Of course, we are not sure what will happen in 10 years. But what we are sure is that renewable energy is being connected in rural areas where a few people are living. So anyway, even if the consumption is higher, there are not so many people. So it will not be a dramatic increase of consumption in these areas. I had a second question here, Evelyn?
No.
Okay.
Thanks.
Okay, so the idea is that the curtailment, we don't have to do so much curtailment so often. So this is why we have savings. So automatons for fast, last time to decide and corrective actions. Okay, last time to decide is we want to take actions as late as possible. So latest time as possible. So to operate the grid, there are two ways. Either preventive, it's here. You organize the dispatcher, the control room, they organize everything day ahead, or a few hours ahead, so that in any case, even if there is some vehicle going to a pylon and then the line falling down, okay, so whatever happens, to organize everything so that whatever happens, flows will stay below their limits. Okay, these are named preventive actions. And in that case, we need to take large margins to cover uncertainties. Okay. Today, in some areas in France, near Poitiers or Niort, day ahead, people see okay, tomorrow the lines will be at 70%. Fine. And in real time, that day, they see 100%, and they had to switch off a lot of wind farms. Okay, this is not bad work of weather forecast. This is not bad work of wind farm generation forecast. It's really because local forecast, local generation forecasts are not it's not possible. Okay, so it's normal to have this kind of uncertainty. So if we want to do everything in a preventive way in advance, so we have to take large margins. So after a fault, if there is a fault somewhere in an equipment, then this equipment is not available anymore. And then it may create overloads on neighboring equipment. And then the fact that we take fast actions is named curative. So after a problem, we cure the problem with curative action, which has to be taken very fast within a few minutes. So the capacity is exceeded for a few minutes, but it will take a few minutes for the line to be too hot. I mean, the heating process is dynamic. So we use this thermal inertia of the metallic equipment to take some very fast curative actions. But then we need some process, some device, some automaton, some software to perform this very fast curative action. So we decided about 5 years ago to go to the latest time to decide framework. And the idea is we want to be lucky. We want to take actions as late as possible, to be lucky in many cases, to benefit of all positive events that may happen. So you have a bit less wind than expected, or a bit more general consumption than expected, or some wind farms are not working for some reasons, or the wind is in the right direction, and then the cooling of the equipment is so good that you can really put 150% of the standard capacity, because the wind is cooling so well that you can really put a lot of power on the line. And then in that case, if we can act very fast, so 15 to 60 seconds, we have only to cover the risk associated to this duration. So we had to cover the 60-second risk. What is a 60-second risk? Is what may be an increase of flow on the line within 60 seconds. Okay, is it 10%, 20%? But we don't know exactly, but we know that if we can act in 60 seconds, we have to cover only 60 seconds risk. If we can act in 15, we have to cover only 15 seconds risk. So we developed zonal approach, zonal controllers from 2 to 50 substations. It's automaton, so they will take decisions automatically. And within this local controller, we have optimization with model predictive control and DC models. So DC models means DC current approximation. So today you may hear about DC grid in some papers, or high voltage direct current, so HVDC lines. It's the fact that the power grid has been running with AC current, AC power, alternative current power for a century already. And now we are putting some direct current parts on it, because for underground or undersea lines, it's more convenient. This is DC. Here, in this slide, DC model means DC approximation. Okay? So this is AC power with DC approximation, and direct current approximation means this approximation is linear. So here we have a linear model in our model predictive control framework, except we will have binary variables, because when we switch off a wind farm, it's a binary variable. The levers, so what can we do? We can use large batteries. So we, RTE, we decided to install, and they are being installed. One is already, one is ready, two are being tested as I am speaking now. So 10 megawatts battery. So if you look in RTE, the smallest lines are roughly 50 megawatts. So 10 megawatts compared to 50 megawatts, it's not that much. But still, 10 megawatts is roughly 10 containers. 10 containers. So it's already we have to buy some land to build them. So we are, as an experiment, we are building, and we will operate the three large batteries, 10 megawatts each, for congestion management embedded in our local controller. So the first lever are batteries. We have, of course, as I already mentioned, wind or solar generation curtailment or limitations. And in some places, it may be useful sometimes to make the flow go right or left to open some lines. We call this topology optimization. We have measurements every 10 seconds and actions every 15 or 25 seconds, depending on the quality of the measurements, if we need. Okay, and this is for submission zones. So today we have 2 zones in real test. In 2021, 7 zones are ready to go. So I already run some simulation on them. I already convinced the people from the control room to accept these ideas. And in 10 years, our estimation is to have 180 zones, each of them being monitored and operated automatically by this zonal control. The scheduling and controller process. So here, the real-time controller is this part here. Okay, running at that time we thought we would have 1 second measurements, so we were expecting to run it every 5 seconds. But in all locations, finally we will get a low-cost 10 seconds measurement. So we will operate every 15 seconds. This is a local controller getting measurements from the locally measurements from the grid and taking actions every 15 seconds. And then we have some upper level scheduling. Mostly for the moment, this is used for the batteries. So for the batteries, we have to prepare the battery. So if there will be a congestion in the future, if we expect a congestion, we have to empty the battery, to discharge the battery in advance. During the congestion, the battery usually will be used to charge, to have less power on the grid. It will the battery will be charged by the local controller. So it was discharged before the congestion by the scheduler, by the scheduling part here, charged during the congestion by the real-time controller, and then after the event, after the event, then the battery will come back. Will be set back to its reference level by this scheduling process. This scheduling process is performing security analysis on the full French grid using all, and it's embedded in all the hours ahead security analysis software of the company. We also have some not technical, but I would say political constraints that the 3 batteries have to be balanced, so have a sum of power equal to 0, not to interfere with markets. I mean, it's a few amounts, but some people are really market crazy, so we have this smooth constraint. Okay? So the priority is to avoid to do some renewable energy curtailment. But if we have a congestion only in one area, then we will use the two other areas to compensate and to have the balance of the 3 batteries. So the real-time controller has to enforce limitations to capacities of the lines, either permanent limits here or limits coming from dynamic line ratings, and to follow orders for the higher level, for instance, discharging the battery before congestion. Data every 10 seconds and actions every 15 seconds. The MPC formulation is roughly this one. And the idea of model predictive control is that, first of all, you have a model. Okay, so we have embedded in these equations, we have some model of the power flow equations. We'll say a few words just the model predicts the behavior or gives a prediction of the effect of the controls that we will take. We don't really have any forecast in it. Keep in mind that we have 60 or 100 seconds horizon. So there is no forecast of load, consumption, or generation. There is no local forecast for every city or every village of all of this available for 20 seconds, 20, 60, 100 seconds. Okay, so we don't have any injections forecast. The only forecast we have, basically, is the fact that if we send an order to a wind farm to switch off, if we send this order 20 seconds ago, and if it takes 45 seconds, then in 25, it will really be at zero. Roughly, that's the same. That's the only forecast we have. Okay. And also, in this model predictive control framework, we have an optimization for, let's say, 60 or 120 seconds. But we send the order only for the first time step. Okay, so if we have to send a wind farm curtailment order, it's 45 seconds in advance. If it's for battery or for line opening, it's immediate action. Okay, so it's totally zonal, as I say. Okay, so here maybe a word here. You may remember the complex equations of the flow on the line. Here, we use the DC approximation one, which is linear. So the flow here is a real variable, megawatts only. The voltage is assumed to be constant. The losses are assumed to be zero, and we only have the reactance part. And so the variables here are the flow on the lines in megawatts and some phase angle for each node. And here, this is linear, so x is a constant. Okay. So we have simple DC approximation linear equation. We would like to do this using optimal power flow in AC. Okay. So maybe in 10 years or 20 or 100 years, this quadratic non-convex problem will be solved as well as linear problems, and then we may move to AC optimal power flow at this stage. But for the moment, we need to rely on very good, very high quality on the software that we know that it works, or we understand why it doesn't work. And for the moment, that is not the case with AC optimal power flow. Even with interrupt methods, sometimes we don't have results and we don't know exactly why. So for the moment, we cannot in real time use something else than linear programming or mixed integer linear programming. Yes, I have a question.
Is the DC running or AC? But are you modeling it?
Yeah, so the power is AC power, okay, and it's a DC approximation. I think I said everything here, so I will.
Oh, that's great. Then we have time
No,
for
no.
questions. Oh,
No,
sorry. Okay.
So this is an example. This is an example of an area. You see some cities: Poitiers, Niort. Okay, Limoges is right here. Okay, and we have overloads here. I mean, in this area already, there are much more overloads than If everything is at 100%, we have much more overloads than on this graph. So here is the variation of a wind farm, which is roughly here. Okay.
So it's only wind farms, or are there also some kind of solar?
Here it's mostly wind farms. It is rare that we have zones with both. Usually there is a few wind farms everywhere, but very few, and we have locations which are mostly wind farms. But usually wind farms are small. There is one zone in France, not far from here, in Gap, in Haute-Durance Valley, where it's mostly solar, but usually it's mostly wind.
Can you say which variables are discrete and which are continuous? Discrete, that's the wind farms and the solar.
So discrete is if you switch off totally a wind farm or a solar farm. If you have a limitation, it's continuous.
Sure, but you can ask them to just reduce, or
it depends. In some locations, you have only a switch off order possible. In some locations, you may go for a limitation in percentage to reduce. Okay. It depends on the way the connection is made. We have to go through the distribution company, so it depends, and it may evolve in the future.
What are the other variables?
The other variables are the battery power, which is continuous, and the opening of a line, which is discrete. Okay, if we open a line, okay, then this line is off. Okay, imagine that here. Imagine that here, okay, you have a major congestion on this small line here. For some reason, this line capacity is half of all the other one. Okay. Imagine that you have a major congestion here because of some flow coming from south to north. Then, if you open this line, it solves everything. Okay. That's really the good thing to do in some cases. Okay, to simply switch off, and then the major flow coming from Spain to northern France will stay on the 200 kV, 400 kV grid, and will not come through this 90 kV grid. Yeah, opening is switching off. Yes. In electricity, when you open, the power cannot go. It's not like a door. Open means switch off.
But isn't it then the main solution to judge this opening lines?
Sorry?
Isn't it the main solution to the congestion problem, opening a line?
So first of all, this one here has been upgraded. So now it's almost the same as others. Okay, it has been for several years, but now it has been upgraded. If you have a lot of power, normally, if you have a lot of power everywhere, if you open some lines, the global capacity is lower. So if you have a lot of power everywhere, people start thinking that the best way will be to switch off, to curtail, or to do some limitations at the right locations. This is why there is optimization. If it's not so, I mean, there is a lot of power, but not so much, then lines opening may be useful. Or you may have also this line opening when you have in this small area here, if you have not so much wind farm producing now, but large flow coming from Spain to northern to Belgium, going through there, and there is so much on the 400 kV grid that a part of it is coming through the 90 kV. Okay, so normally you keep the lines connected, so closed means connected, they are operating. In some cases, it may be better to open them. Okay, so this is a fast increase of generation. Okay, it is a wind farm here, and you see it's a 24 megawatt wind farm. And in 5 minutes, you go from 0 to, or you have 17 megawatts increase. Okay, so the increase is very high. If you look at statistic of this wind farm over 1 year, you can see that and I mean, we made this study checking everything manually with your own ACE to be sure that there was no artifact in the data. Okay, so you can see at maximum in 5 minutes from 0 to maximum to 24 megawatts. Okay, so these are probabilities, and these are increases in percentage depending on the time. So what is interesting here is the fact that variations in 5 minutes are twice variations in 1 minute. So if you look at this line here and the last one, then the 5 minutes is always, whatever the quantile is always twice as the increase in 1 minute. Okay, this is a proof that we are right to try to act very fast at the latest time and not in advance. And this is a real line, a real flow on the line. And here in this part, there is a 10% increase in 1 minute. Okay, this is an increase in 1 minute here in blue, and we can reach here 8, and this line is 80 megawatts capacity. So we have a +8 in 1 minute and a +24 in 5 minutes. So on the lines as well, the increase is twice as much in 5 minutes than in 1 minute. And this leads us on this line to have a 10% margin. As we can act in 1 minute, we need a 10% margin. So we need to operate the line at 90%. And if the line comes to 91%, as it will take roughly 1 minute to switch off some wind farms, we have to start switching off right now to cover the risk of what increase could happen in 1 minute. So this is an example. So here we have a line coming. This line. This is the small one I showed you, and this is the limit, which is low here, 300 amperes only. And at that time, the software, the optimizer decided to switch off. So this line comes here, and here we have another line. And when there is a switch off of the first line, the current is increased, but this is normal. And then the wind makes increase here. And this is the maximum of these lines. But as you see here, we have some trick on the derivative here. So when it's here, it decides to switch off some wind farm, and we come here. And then there are other increases. And at the end, we are roughly at 90%. This is simulation. So with this kind of simulations, we have the optimization in linear, and the simulation is real AC time domain simulation, very precise tool. These simulations have allowed us to convince people of the control rooms to accept the project. And now this is an example of an experiment. This is real data. Okay, so here, for some reason, there was a bug in the software. In some gateway, so the battery, which is in blue here, was oscillating. Okay, and here we are measuring in red the flow on the line. This line was monitored; it was a test, and thanks to some bug in my software, the battery oscillated. Okay, so we send this order, then this order, then this order. Okay, and what is interesting here is to see that the flow on the line, which is monitored, takes only roughly 2 values here. Okay, we have discrete values on the measurement of the flow. This is a real problem, and as a consequence, if you see the sensitivity, so you see here the battery variation at this time, the battery variation here varies. The battery is in blue from 3 to 6 megawatts, and the impact is always the same, 1.4 megawatts. So the influence, the sensitivity here is varying from 22 to 39%. Okay, this was measured. This comes from test made in November, and this was really unexpected. So we will have to fix this. And here the problem is that the measurements are discrete. The discretization here is 0.7 megawatts. We will do further testing to identify this problem. But have in mind that how to handle this in some optimization model. Okay, so I think I said everything here. Thank you.
Great, thank you. So Yeah, let's start. So we'll start with the questions in the room, and Lynn will help me with first in the room. So Milan Korda first.
So can you speak a bit more about the MPC problem? How many variables you have?
So, but the MPC problem, how many variables? So here you see.
How big it is?
Yeah. So here you see a zone. Okay, for each zone you have a θ1 variable. Okay, the phase angle, and you have a flow on each line. Okay, so here you have roughly, let's say.
So these are the state variables.
Yeah, these are the state variable. The control variable for each node, basically you have one variable to control. The wind farm, or the wind farm are aggregated by each node. Okay, and there is in total here only one battery here in Belak. Okay, only one battery because we have only one in this area. And for a few of the lines, we have a 0-1 variable. Okay, so the problem is small, very small.
Tens of variables.
The number of variables will be a few hundreds.
And how many of them is free?
A few reasons. So we use FICO Express, and it's always solved within less than 1 second. We don't need 10 milliseconds. Okay. Yeah. It was made by Dash Optimization. It belongs to FICO Express. It's similar to Bureau or Cplex. Really similar.
And basically, when you fix the discrete variables, you get standard quadratic programming.
Linear. We use here mixed integer linear programming. Yeah, so you're right here. This is general framework with quadratic, but in fact we have here a linear objective function. Okay. Everything is linearized.
So additional questions in the room.
To confirm,
Introduce yourself.
please stand up. Yes, logic. I come closer.
Yes.
But just talk louder. Right, so just to confirm, your data shows that the longer the time period, the bigger the variations are, like in the network, in load and these things. So it's safer to say, instead of investing more into predicting what the load will be, you invest more into rapid response. Right? But this rapid response, so this is, I just want to be clear on that. It's more important to have these rapid response. That's like your control model. That's where you optimize what to do in a small zonal situation, rather than actually having, how should I say, more data-based predictions of what load will be based on the weather and the people and stuff like that.
We cannot imagine that it would be possible to have this kind of forecast. Okay. If you look at the 5-minute forecast, here, look at there, it's 10-second time steps. So here you have, it's not a long period. Here you have 1 hour or 2. Here you have 2 hours. Okay, imagine that you do half an hour forecast, then you have some lines here. You will never have a forecast of this increase, and here you will never have a forecast of these very fast variations of the flow on the line.
This is a clear example where full control is much better than prediction.
Yeah.
Cool, thank you.
We have another question in the room. Lynn, oh, okay, Provinian, introduce yourself, come closer. Introduce yourself.
Hello, this is Provinian also. One question, the optimal control problem you consider, is this actually a time delay optimal control problem? Are you modeling it like this, or?
Yes, we have time delays. We are really embedding in the MPC optimization problem the fact that if you decide now to curtail, the curtailment will be effective in 45 seconds.
Yeah. Okay, so this is in the MPC.
Yeah. If you want to look for very precise modeling, you can go to the work. It's mostly publication made by Central Supélec. Okay, or you look to my Google Scholar. Okay. But what we do in reality is not exactly what is in the papers. So we have linear objective function, but it's the same idea. Okay, so they are doing prototypes to prove ideas and concepts. We are doing industrial code, and our industrial optimization code is the same used in the software, in the real automatons, and in the simulation. So here we have simulations, and the simulations use exactly the same optimization or MPC framework than the real software. Okay, so this was really a major success of this project to be able to have the same optimization code in simulation and in real time. It's the first time we have it in RTE.
For question?
Yeah, but
Yeah, okay. My last question, is it possible, instead of shutting down, maybe in a big farm, for example, to transfer it somewhere else, pumping up water somewhere else, for example?
This is roughly two questions here. Either to transfer somewhere else. So here behind these nodes, which are transmission nodes, there is a distribution grid, which is operated as a tree, but physically it's meshed, but it is operated as a tree. So they open some bus bar coupler somewhere. So it's operated as a tree, but they may close if there is a fault somewhere. They can switch on something, and then the tree will be changed. Okay, but these are not real-time operations. Okay. And second, in this area, maybe there is a wind farm here. They can move it to the next location, but basically everywhere here is overloaded. Okay, so this is okay. And for storage, you can store with battery. You can store also with pumped. You can pump water in some reservoir to a higher reservoir. Okay, but here in this location, it's flat. Okay, it's near the sea in Poitiers, New York. It's flat.
right, so we're not seeing any question online. I hope this is correct. We're going to leave for private discussion, further questions by Didier and others. Maybe we'll make space for the next two. Thank you so much for
Thank you.
this.